Fermat's last theorem.
Fermat's last theorem is one of the most famous problems in the history of mathematics, and it all started with the ancient Greek mathematician Pythagoras, who created its basis with his Pythagorean theorem. The Pythagorean theorem was the formula a squared plus b squared equals c squared, which states that in a right triangle, the square of the hypotenuse will equal the square of the sum of the square of the other two sides. And this led to the idea of Pythagorean triples, a set of three positive integers which will fulfill this formula.
Diophantus was an ancient Greek mathematician who developed a method to determine primitive Pythagorean triples. So these are Pythagorean triples in which a, b, and c have no common divisor greater than 1. Diophantus wrote this discovery along with many other algebraic equations, solutions, and notations in a book titled Arithmetica. Pierre de Fermat later wrote down Fermat's last theorem in this book.
Pierre de Fermat was a French lawyer and mathematician who lived in the 17th century. Though he was a lawyer, mathematics was emerging as a more prominent field of study at the time, but not as a career, so Fermat did mathematics as a hobby. Arithmetica was still considered one of the best books about mathematics at the time, so Fermat read it and noted his ideas in the margins. And one of these ideas was Fermat's last theorem. When reading the book, Fermat wondered what would happen if n did not equal 2. So, see, for Pythagorean triple, many ABC may be any positive integer, but n must always equal 2. Fermat theorized that if n were to be greater than 2, there would be no positive integers for which x to the power of n plus y to the power of n equals z to the power of n, and this idea came to be known as Fermat's last theorem. And along with this theorem, Fermat wrote that he created a proof, but it was too long to include in the margins, and it was unsolved for over 300 years.
Then, in the 18th century, Leonhard Euler, who was one of the most famous mathematicians of all time, developed proofs for many of Fermat's ideas and ran into Fermat's last theorem. He managed to prove Fermat's last theorem for n equals 3 by showing that x cubed plus y cubed equals z cubed had no positive integer solutions, and he did this by using factorization.
Sophie Germain expanded on these ideas, and she came up with a new way to approach Fermat's last theorem. So what she did was she noticed that if the equation were to have a solution, then the numbers x, y, and z would have to follow strict patterns when divided by another prime number, which she called q. She realized that by choosing a special kind of q, she could prove that certain versions of this equation were impossible, and therefore she was able to work with many values of p by finding q for each scenario, therefore proving Fermat's last theorem for many prime numbers under 100.
Ernest Kummer developed the theory of ideal numbers, which restored unique factorization in these fields. And Kummer's works, Kummer tried to prove that Fermat's last theorem was true for regular primes.
The next major breakthrough came when Gerald Faltings solved a mathematical problem crucial to the development of the modern approaches to Fermat's last theorem. Specifically, he worked on the Mordell conjecture, which was a conjecture that focused on algebraic curves and stated that if a curve has a genus greater than 1, then it has only finitely many rational points. And in 1983, Faltings proved this conjecture, and his result is now known as Faltings' theorem, which states that for every exponent, there exists finitely many primitive solutions.
Later, in post-World War II Japan, Yutaka Taniyama was working on elliptic curves, which is an equation such as y squared equals x cubed plus ax plus b, and he proposed the basis of what later came to be known as the Taniyama-Shimura conjecture. Goro Shimura was working with Taniyama, and he helped refine the Taniyama-Shimura conjecture to come up with the statement that every elliptic curve is modular, which a modular form is a complex function with special symmetry properties.
In the 1970s, Yves Hellegard had the idea that the solution to Fermat's last theorem would be able to form an elliptic curve. Therefore, according to the Taniyama-Shimura conjecture, it must have a modular form as well.
Then Gerhard Frey, who heavily studied these Hellegouw curves, proposed that these curves are not modular and therefore would violate the Taniyama-Shimura conjecture. And due to his work, these curves soon began to be known as Frey curves.
A decade later, French professor Jean-Pierre Serre came up with a rigorous statement that, if proven, would prove that the Frey curve was not modular. This came to be known as the epsilon conjecture. So if the epsilon conjecture was proven, then one only had to prove the Taniyama-Shimura conjecture for the Frey curve to prove Fermat's last theorem.
The tipping point came in 1986 when American mathematician Ken Rebate proved the epsilon conjecture after having a breakthrough after collaborating with Barry Mazur one day.
Barry Mazur helped Ken Rebate, but he also heavily helped mathematician Andrew Wiles prove the modularity lifting theorem through his work on the deformation of Galois representations, which is what Barry Mazur studied as a mathematician. He also developed a proof for the Iwasawa main conjecture, which was used by Andrew Wiles to prove the modularity of the Frey curves and was essential for proving Fermat's last theorem. Richard Taylor, who was a student of Andrew Wiles, also helped him prove the Taniyama-Shimura conjecture and assisted Andrew Wiles in developing new techniques in order to fix the gaps in his proof for Fermat's last theorem after it was found that his existing proof had errors.
So Andrew Wiles is credited with proving the Fermat's last theorem and he did this by proving the Taniyama-Shimura conjecture for semi-stable elliptic curves. He chose to focus on semi-stable elliptic curves because Frey curves are this type of curve, and they behave nicely at all prime numbers. And so by proving that all semi-stable elliptic curves over the rational numbers are modular, he finally managed to prove Fermat's last theorem after over 300 years of mathematicians trying their best. And these are our references.